All right, let's talk linked lists. Deleting an item? Sounds simple enough, but what if I told you that you could only delete the very last one you find? Suddenly, it's not so simple, is it? This little twist turns it into a really cool programming puzzle, and today, we're gonna solve it together. Let's dive in.
I mean, really think about that for a second. Finding the first matching item in a list, that's a walk in the park. But how in the world do you know you found the last one? You can't be sure another one isn't just hiding around the corner, right? That's the real challenge we're going to crack today.
So, here's how we're gonna tackle this. First, we'll dig into why this is so tricky in the first place, what I like to call the one-way street problem. Then, we'll unveil our secret weapon, the two-pointer strategy. After that, we'll translate that logic into some C code, see how well it performs on its report card, and finally, we'll wrap it all up with the key things we've learned.
Okay, first up, the one-way street problem. Let's really get to the heart of what makes this specific task, well, harder than it looks. You see, the whole issue comes down to the fundamental nature of a singly linked list. The best way to think about it is like a train. You can hop on at the engine, that's the head, and you can walk through all the cars towards the caboose or the tail. But here's the catch. You can't walk backward. It is strictly a one-way trip.
So let's look at a concrete example right here. We've got a list that goes 10, then 20, then another 10, and finally 30. Each of these boxes, or nodes as we call them, only knows about the next one in line. And see that last node? It points to null, which is just the signal for, hey, this is the end of the line. Our mission is to delete that second 10. Now if we wanted to delete the first 10, piece of cake. We find it, and we just tell the head, hey, skip this guy and point straight to the 20. Easy. But deleting that last 10, that's where we hit a wall. When we get to that second 10, we're kind of stuck. We have absolutely no idea if there's another 10 coming up later. And because it's a one-way street, we can't just peek ahead and come back. We'd lose our spot.
So, how do we get around this? Well, we're going to use a really clever technique called the two-pointer strategy. This is our elegant game plan, our blueprint for solving this thing.
And here's the absolute most crucial rule we have to follow. We can't just stop and delete something the moment we find it. We are literally forced to walk through the entire list first. Only after we've seen every single node can we confidently turn around and say, aha, that was the last one I saw. And only then can we actually do the deletion.
So here's how this strategy works in practice. We're going to create two special pointers that act like our bookmarks. We'll start at the beginning and walk through the entire list, from head to tail. Now, every single time we find our target number, we just move our bookmarks to that spot. If we find it again later, no problem, we just move the bookmarks again. By the time we get to the very end of the list, where are our bookmarks? They're sitting right on the last occurrence we found. Perfect! Now we can finally perform the deletion.
All right, that logic sounds solid, right? Now for the fun part. Let's see what this actually looks like when we translate our blueprint into a working C program.
Okay, first things first, let's look at the basic building block of any linked list, the node structure. The easiest way to think of each node is as a little box. This box holds two things. First, a piece of data. In our case, it's just a number. And second, a pointer. And a pointer is really just an arrow, an address that tells us exactly where to find the next box in the chain. Now for the setup. We create our two special bookmark pointers. We'll call them node to delete and prev node, which will track the node right before it. And we initialize them both to null. This is a super important safety step. Null basically means pointing at nothing. So if we finish our search and these pointers are still null, it's a clear signal that we never found a match to begin with. Next up is the engine of our whole operation, a while loop. This little piece of code is what guarantees we start at the head and keep marching forward one node at a time until we hit that final null at the end. This is how we make sure we see every single thing in the list.
And inside that loop is where the real magic happens. We've got a simple if statement that checks, does the data in the current node match the key we're looking for? If it does, boom, we update our two bookmarks to point to this new location. And you know, if we find another match 10 nodes later, who cares? We just update the bookmarks again. We're constantly overwriting them, which is exactly what we want. It guarantees that by the end, they'll be pointing to the very last match we saw.
And finally, once the loop is all done, meaning we've reached the end of the list, we do one last check. If our node to delete pointer isn't null, that means we found our key at least once. So we use our prev node pointer to basically reroute the list, telling it to skip over the node we want to delete. We're effectively cutting it out of the chain, and then of course we free up that memory.
So we've built it and it works, but the next big question is it any good? Let's give our solution an efficiency report card. How does it stack up when we look at time and memory?
And hey, our report card is looking pretty great. For time complexity, it gets an O of n. All that means is that the time it takes to run is directly tied to the number of nodes, n. And that's basically the best we can do, since we have to check the whole list. Now, for space complexity, it gets an O of 1, which stands for constant space. This is fantastic. It means we only use a tiny, fixed amount of extra memory for our pointers, and it doesn't matter if the list has 10 nodes or 10 million. It's super efficient.
Let's just zero in on that time complexity for a second. O of n, or linear time. This is really the signature of a top-notch algorithm for this specific problem. You literally can't do better because you just have to look at everything once to be absolutely sure you found the last one.
Okay, let's bring it all home. What are the big, key takeaways from our little journey here?
So here's what you should remember. First, that one-way street nature of singly linked lists is what creates these fun, unique challenges. Second, that two-pointer technique, it's a super powerful strategy to have in your back pocket for tracking nodes. And finally, we learned that the most efficient solution runs in linear time, O of n, and uses constant extra memory, O of 1. It's fast and it's lean.
And that brings me to one last thing for you to chew on. Our solution was all about being extremely memory efficient, right? O of 1 space. But what if you didn't have that restriction? What if you were allowed to use more memory? How would that change your approach to solving this? It's a classic trade-off in programming, and definitely something worth thinking about. Thanks for joining me on this one.